Hello all, I'm Dr. Nusharwan. I'm the chair of IEEE MTT EMC and CAS Joint Chapter Islamabad. I welcome you all on this webinar series. I'm also working as assistant professor at Research Institute for Microwave Millimeter Wave Study, also known as RIMS, at National University of Science and Technology, Islamabad, Pakistan. Um, we are located in Islamabad. Islamabad is the capital of Pakistan. It's one of the very well managed capital among the world, and it also have the business hub as well as the natural beauty. And this is the same city where we will host the first IEEE International Conference on Microwave Antennas and Circuits, also known as ICMAC 2021. And I hope you will join us in this conference to present your research and talks. As I mentioned earlier, I belong to National University of Science and Technology, Islamabad, Pakistan. The NUST has several campuses. This is a bird eye view of Islamabad campus, and the RIMS is located here. So this research institute for microwave millimeter wave studies, RIMS, is a specialized postgraduate institute that offers master's and PhD degrees in electrical engineering with a particular focus on RF and microwaves. We have state-of-the-art research facilities such as anechoic chamber that start from 800 megahertz to 40 gigahertz. We have both near field and far field setups. For antenna characterization, we have EMC compliance pre-compliance lab as well. This lab is basically used to perform the pre-compliance testing, also used to teach the student the EMC related issues. We also have the microwave research and antennas lab and PCB fabrication lab under one roof. The purpose of all these facilities is that apart from just learning the theoretical concept, the student will actually design, fabricate, and test the antenna at the same place. So this gives them an opportunity from the design point of view, also from the hands-on experience point of view. So we have initiated a webinar series in March 2020 in view of COVID-19 pandemic. We have a number of webinars in the past, and all these webinar videos are available on our YouTube channel known as RIMMS-NUST. So you are requested to please subscribe and like the videos and view the videos that we post on this YouTube channel. So today we are very pleased to host Dr. Syed Aziz Shah from Coventry University, UK. His talk title is RF Sensing for Healthcare Technology. A few words about Dr. Syed Aziz. He's currently an associate professor of mobile health at the Center for Intelligent Healthcare in the prototype design and testing team. Dr. Syed is working on software-defined radios to develop a prototype that can monitor activities of daily livings of elderly people and detect anomalies in the respiratory rate at homes or care centers. Dr. Aziz's research work spans across multiple disciplines, including wireless sensing, radar technology, software-defined radios, machine learning, cybersecurity, and intelligent healthcare technologies. Dr. Syed has co-authored and co-authored more than 42 technical articles in top-ranked peer-reviewed multidisciplinary journals, including 3 transactions papers focusing on intelligent healthcare. In addition, Dr. Syed has taught numerous graduate and postgraduate modules and supervised students at higher education level. His research interests include but not limited to mobile health, prototype designing, radar sensing for healthcare technologies, non-invasive fall detection, psychological measurements, remote patient monitoring, wireless sensing, machine learning, and cyber security for intelligent healthcare. So without any further delay, I request Dr. Syed to please proceed ahead and start his webinar. Over to you, Dr. Syed. Thank you. Dr. Syed, I think your mic is off. Can you please turn on your mic?
Can you hear me, please?
Yes, I can hear you and everything is fine. You may proceed ahead.
Yeah, thank you so much, Dr. Nishwan, for introducing me. So, yeah, my name is Syed Aziz Shah, and Like Dr. Noshirwan has introduced, I'm working as an associate professor at Health Care Technology and Innovation team at Center of Intelligent Healthcare, Coventry University, UK. So today my topic is about radio frequency sensing for healthcare application. So the core idea is that I would like to present the background and some of the examples, and then the open challenges that we face when we apply wireless sensing with regards to healthcare applications. So a bit about myself. So I've completed postdoctorate from University of Glasgow in wireless sensing for healthcare applications. My PhD was from Shedian University, China, in similar field, and also my master's degree was in wireless networks and electronics from Linköping University, Sweden. And I've also completed the undergraduate studies from Comsats University, Pakistan. So my research interest, so I would like to shed a little bit light about my research background. So like I mentioned, my research interest, so it comprises in two sections. Number one is wireless sensing for healthcare and well-being. So there, what I'm doing, I'm looking into the non-invasive, non-contact RF sensing to monitor patients with neurological disorder and detect critical events such as freezing of gait in Parkinson's or wandering behavior in dementia patients, fall detections, so on. And we have monitored the hydration level of patients, for example, in patients or even in sports person as well. In wireless sensing for agriculture technology, so what we are doing, we are applying terahertz sensing in conjunction with machine learning algorithm to detect moisture content and also water contamination. So achievement in this regard, I have more than 42 publications in top rank peer-reviewed journals, including 3 transactions, and also my work has been cited more than 500 times. So a little bit about the research center, what we are doing. So this research center, Center of Intelligent Healthcare at Coventry University, it was launched last year in 2019, August 2019. So the core idea was how we can use intelligent healthcare, for example, bringing multidisciplinary team, for example, nurses, doctors, uh, then people from engineering and computers background, so that they can sit together and probe into some of the open challenges that people face with regards to healthcare technologies. So, so in this context, what we are looking into the new approaches, new technologies, in conjunction with support evidence to help people who can live a healthy, active, and independent life. So that's the core theme of Center of Intelligent Healthcare. This is our Center of Intelligent Healthcare. It is fits into three main themes. Number first is epidemiology and evidence-based healthcare. The second one is behavior implementation science. And the third one, the theme where I'm working is that's the HTI theme, or healthcare technology and innovation theme. So the healthcare technology, so what we are doing, we are working in multidisciplinary field. So our team works into the physiological measurements and also in designing application of advanced biosignal processing, computer modeling, and big data analysis. Apart from there, some of our colleagues, they're also working on macro and nano. And then acquiring this data, we have also a couple of our team members who are working on the development of state-of-the-art machine learning algorithms, that how the data acquired using these sensors can be applied and they can be classified for various diseases. And then the area where I'm working on like 5G wireless sensing for smart mobile healthcare. And I've already given brief description about myself as well. And in the end, so we have also team who look into the prototype usability and also co-creation design as well. So that was a little bit marketing about our research center and the HTI theme in particular. So now I would like to come to the main topic, which is RF sensing for healthcare technologies. So the main motivation behind using RF sensing is that, as we are aware that wireless sensing, it is available everywhere. Wireless signals there are available everywhere. For example, in parks, in buses, in homes, in shopping centers, in hospitals, and they are capable of monitoring different activities. By different activities, I mean that these wireless signals can be used to be used for intrusion detection. For instance, if someone is sneaking into your house and you want to catch a thief, and also these signals can be used to monitor patients as well for different diseases. And wireless sensing can also be applied in search and rescue operation as well. So my main focus on today's presentation is to give a brief introduction to how wireless sensing can be applied in remote patient monitoring. So the core idea is, for instance, like how we can use these signals to monitor activities of daily living of patients. For instance, if we have a transmitter here on the bottom and receiver here. So if the person is sitting, we will be receiving signals in line of sight propagation, the one in black. Some of the signals will strike with the walls, the one in the blue, and some of the signal will also strike the patient's body, which is in red. So as the person moves from sitting position to standing, the signal propagate path changes as well, and which is evident here, like the signal propagation path changes from red to blue. So the signal that is received while the person was in sitting position will be different from the person that is sitting in standing position. So we will have, so what it implies, so the phenomena is like each body movement induces a unique imprint on the wireless channel, so that we can use to infer different activities of daily living and to identify different disease symptoms that is related to large scale body movement or small scale body movement. So why do we need to use wireless signals to monitor patients? Like, because we can also use camera-based system as well, but camera-based system presents so many limitations. For instance, it raises privacy concern. It is line of sight dependent, so the person has to be in line of sight, and also uh, it is also like the room, the camera-based system, they are also light dependent as well. Because so with regards to that, the technical challenge that camera-based system provide is it is computationally expensive as well. So these are like 4 or 5 limitations that camera-based system presents. So that's why people these days do not rely on vision-based systems. So in this regard, the first technique that we can use is a received signal strength indicator to monitor patients or activities of daily living. So like I mentioned before, for instance, the received signal strength indicator, it is the averaged out signal that is received through line of sight and non-line of sight propagation. So if we have a transmitter on left side and receiver on right, so as we can see clearly, if the person is standing still, we might have receive an imprint such as this one. But as the person starts moving or walking, we'll have a signal such as the one below. So visually, these signals are different as well. But the problem with received signal strength indicator is we only examine one received signal. So let's suppose if the signal is lost for a period of time, so we might have some of the critical events. There is high likelihood that some of the critical events such as fall may go undetected. And the RSI signals are also susceptible to noise as well. So if there is movement in surrounding, it will, in that case as well, it will present false alarms. And this signal is also highly variable as well, even in static conditions. So in this context, instead of using the received signal strength indicator, we can also use channel state information. So the core idea is, for instance, I think most of us, we use Wi-Fi routers at our homes and everywhere. And it's a ubiquitous device. How Wi-Fi works? Wi-Fi, as we all are aware, Wi-Fi works on multiple frequency signals. So instead of transmitting one signal, so what it does, it divides the frequency spectrum in different subcarriers. For instance, in Wi-Fi, IEEE 802.11, according to these standards, it splits the frequency spectrum into 64 subcarriers. So instead of analyzing one received signal strength indicator, we analyze multiple frequency signals. So just in case, like if one or more than one signal is lost, so there's high likelihood that we might receive the remaining wireless signals that we can infer to monitor different patients. So we can see here, like if the person is standing still, so we can analyze multiple frequency subcarrier which are static, and as the person moves, it induces change in all of the subcarriers. So like I mentioned, instead of analyzing received the variances of amplitude information using RSSI, we can use the amplitude and phase information of challenge state information to infer different activities of daily living. In order to do that, the another advantage of using challenge state information is we do not need to use any expensive device. We can leverage on low cost off the shelf commercially available small wireless devices such as like Wi-Fi router. It is ubiquitous, present everywhere, and also network interface card, so it doesn't cost more than I think 10 to 15 US dollars. So that network interface cards we equipped in a desktop computer and then wire it with an omnidirectional antenna. So using these, I think 4 small wireless devices, we can extract the channel state information within an indoor environment. So the proposed model that we proposed previously, it was the activity-based. The human activities were correlated with RF signals. So on the signals on top right over here. So these are the variances of amplitude information of channel state information extracted when the person was moving in indoor environment. So on y-axis we have the number of packets, and in each packet we have 64 subcarriers, and y-axis we have the change in amplitude information. So this model, the channel state information or CSI model, it presents high classification accuracy. Some of the examples and the experimental setup of using Wi-Fi signal is the one on the left. So what we do, so we deploy Wi-Fi router there like anywhere in the room. So because the Wi-Fi router uses an omnidirectional antenna, so it can detect signals in line of sight and even in non-line of sight as well. So I transmit these OFDM subcarriers, and then a person like moving back and forth or performing activity in indoor environment, and then an omnidirectional antenna wired with a desktop computer. So these signals that are received, the variances of amplitude and phase information. So what we did, we performed the continuous wavelet transformed on these raw CSI signal to extract these images. So each column indicate different activities. For example, when the person is walking slow, walking fast, sitting down, standing up, voluntary stop, and then detecting freezing of gait in Parkinson's. So what freezing of gait is? Freezing of gait is for if a Parkinson's patient is moving back and forth. So all of a sudden, the patient experiences as if his or her feet are glued to the ground. So the upper body tries to move, but the feet doesn't move. So this phenomenon is called freezing of gait. So what we did, we put the classifier to the test, and so what we did, we asked the volunteer to do the voluntary stop and then mimic the freezing of gait for us. So as we can see, for a specific frequency subcarrier, each body movement is inducing a unique change in the wireless medium, which is evident in different colors. Voluntary stop, sitting down, standing up. So the signal that we acquired using voluntary stop and freezing of gait is quite different. So we used continuous wavelet transformed on this time history of different CSI packets, and then using the deep network classifier to classify activities of daily living. So this is the first example of using Wi-Fi sensing to monitor freezing of gait and activities of daily living in Parkinson's patient. Moving on to next slide. Yeah, so the another example is, so the first one was to monitor large scale body movement, for example, monitoring like different activities, sitting down, standing up, freezing of gait, voluntary. So these were large scale body movement. Moving on to the small scale body movement, for example, detecting an intricate body movement such as chest movement. So we can also use channel state information to detect chest movement and monitor a normal and abnormal breathing rate. So we used the similar experimental setup, but over here we used a variable sensor as a reference sensor so that we can compare the breathing rate, the normal and abnormal breathing rate that we obtained using Wi-Fi signal. The one on bottom right over here. These are the normal and then abnormal breathing rate obtained using Wi-Fi signals, and then the one on the left is using variable sensor. So we can see there's a quite synergy and correlation between these two signals. So we can also use Wi-Fi signals to detect sleep apnea. So see, sleep apnea is a phenomenon where patients all of a sudden experiences like short of breath or stopping of breathing all of a sudden. So this can also be used to detect small scale body movement, Wi-Fi signal. Moving on from Wi-Fi sensing, the RF-based radar sensing. So we have also used a radar sensor to monitor activities of daily living. So the advantage of using radar sensing that presents over the Wi-Fi sensing is that Wi-Fi sensing non-line of sight propagation. But the problem with Wi-Fi sensing is that the data is non-portable. For instance, if the for instance, if a data is acquired in one geometrical location, so we cannot use that data to import it to another location and to detect like similar activities, for instance, fall or sitting down, standing up, because the channel state information changes greatly if there is any displacement in the movement. For instance, like if a ceiling fan is running or the furniture is displaced. So the radar sensing, because the beam is very narrow, and in addition, radar sensing also relies on the reflected received signal rather than the channel state information. So the micro Doppler signatures that are usually used to monitor different activities. So for instance, these were 10 different activities that we used in indoor environment to monitor activities of daily living or of um, of elderly people. So in this context, for instance, similar to Wi-Fi sensing, radar sensing can also be used to monitor the intricate small-scale body movements such as chest movement. So we can see here, like when the person was moving, breathing normally, then stopping of breathing, and all of a sudden, like exploding all the air that was pumped into the lungs. So it can also be used for elevated breathing rate. And these are on to the right. These are different microdoppler signatures obtained from different activities. Some of the um, radar sensors that we have used. So for breathing, we have used UWB, X-band radar, and for large scale body movement, we have used a frequency modulated continuous wave, 5.8 gigahertz radar. This is one of the examples that this work was published. We have used 5.8 gigahertz FMCW radar to monitor activities of daily living. So the core idea was to develop a generalized system where activities can be monitored across different rooms, and then this data can be imported to another unknown location where we can detect falls. So in this context, I've only presented 4 rooms over here, but later on we conducted these experiments. We expanded these experiments to 9 different locations. So what we did, we collected data inside University of Glasgow at 4 different locations, A, B, C, and D. And later on we went out to elderly care centers, North Glasgow Homes and Age UK, West Cumbria. So in total in this experimental campaign, we recruited 99 volunteers that involved healthy individuals and also elderly people. So the minimum age, I think it was, I don't know, between 20 or 25, but the maximum I remember was 98. We monitor activities of daily living of elderly people. These are different microdoppler signatures obtained for different activities. For instance, A1 is when the person is moving back and forth. A2 is when the person is sitting down, and A3 is standing up. So these, what we did, like we combined the data at 3 different locations, A, B, C, and D, and then you imported that data to room D to test the classifier, and then we shuffled the scenarios. So these were different accuracies that we obtained at this moment, because this work was conducted uh, more than a year ago. So later on, we improved all these accuracy and the performance of our system. So the work is still under review, but that was just to lay the foundation for a generalized system. This work was published in a radar conference last year. Then moving on to, because the Wi-Fi and radar sensing presents like so many challenges. For instance, radar, yes, it works best when any activity or the patient is within line of sight, but any activity that is in non-line of sight go undetected. Wi-Fi sensing can detect line of sight and non-line of sight activities, but the problem with Wi-Fi is, like I mentioned before, the data is non-portable. So in this context, what we did, we move on to the software-defined radios using universal software-defined radio peripheral. So this one to the left, we used this USRP as a transmitter, and the one to the right we use as a receiver to monitor different activities. So the radars, the USRP software-defined radar, the advantage is flexible. So we can use self-defined antennas, for instance, like the high gain antennas where beam is narrow, or we can also use omnidirectional antennas to detect non-line of sight activities. And also the network interface cards I mentioned before, Intel 5300. The problem, the one of the limitation is that it only reports 30 OFDM subcarriers instead of 64. So here we can, in real time, we can increase or decrease number of subcarriers. From 1, we can increase up to X, or it depends on like one's choice. And also we can increase or decrease the power level as well as per our desire. So these are the some of the advantages that a software defined radio presents, for example, in terms of modifying the operating frequency, signal, transmitting power, and also number of subcarriers. So what we did, this is just a demonstration of when the person was performing sitting down activity, moving. So this can also be used to monitor large scale body movement and also small scale body movement as well. Some of the examples, these are the channel state information, the variances of channel state information for sitting down activities, standing up activity, and then first performing walking activity and then bending down. So we can see each body movement is inducing a unique CSI imprint. Moving on to the small scale body movement, we can also, similar to Wi-Fi and radar sensing, we can monitor different breathing rates. For example, shallow breathing rate, when all of a sudden person is breathing very slowly, or person stops breathing, and also normal breathing rate. Different, each color indicates a different CSI subcarrier. In the middle is normal breathing, and then at the end we have elevated breathing, or heavy breathing as well. So these are the results obtained using software defined radios. So moving on, like so this is the work so far that we have done, but this work has also like so many limitations, because we believe we have just scratched the surface. It was just tip of the iceberg, I think, because we believe the work that we have conducted so far is reactive. So it's we are identifying or detecting an activity that is occurred. So what we would like to do, we would like to move from a reactive healthcare system to proactive. For instance, to instead of like detecting critical events such as falls or freezing of gait or maybe wandering behavior in dementia patients, we would like to analyze some of the movements that leads or that leads to these falls. For example, monitoring gait patterns that would lead to a fall activity, or even a freezing of gait. So alert the caregiver or even the patients before an activity is occurred. So again, these are some of the limitations and how we would like to see ourselves in next 10 to 15 years, to be proactive and predictive rather than reactive. Yeah, lastly, so again, a little bit of marketing about our HTI team. So we have, this is our, these are pictures of our team. So we have 2 professors, Professor Ding Cheng, who is our team lead, and Professor John Allen, who has recently joined us, and then myself as an associate professor in Zhengtao, and we also have assistant professor, permanent research fellows, and also prototype design and usability people as well. So we have just started, and we are growing in number because it has been nearly more than a year that since we started. So this is the one on the top. So this is our the intelligent RF sensing fall and health prediction data set. This is the radar data set anybody can use. So it, like I mentioned before, it has a data set of 99 volunteers with different age group and different genders as well. So anybody can download this data and try to utilize it. In addition, we also have one fully funded PhD studentship available. So we are accepting applications from worldwide. So if anybody is interested there, please feel free to contact me. We also have like a different national and international collaboration landscape. For instance, we are working closely with Angela Ruskin University, then James Watt School of Engineering, my previous university, University of Glasgow, of course. And so different universities nationally, internationally, and also we are working closely with University Hospital Coventry in Warwickshire, and some of the industry people as well. For instance, National Instruments, Huawei, Ericsson, and in addition, we are also working with residential care homes, Age UK West Cumbria, and North Glasgow homes. Sorry. Yeah, so that's all. Thank you so much for listening. If anybody has any question, please feel free to ask.
Thank you very much, Dr. Aziz, for your talk. I have few questions on the list. The first question is, what challenges and opportunities are there by using millimeter wave radar for remote vital signs monitoring?
Yeah, that's very interesting question. So for millimeter wave radar, so as you're aware, because for millimeter wave radar, the frequency increases. So when the frequency increases, the wavelength decreases. So as the wavelength decreases, the range resolution also increases. So for instance, instead of monitoring large scale body movement, we can go to the intricate body movement. We can also, instead of detecting chest movement, we can also detect the normal and abnormal heartbeat patterns as well. So as we decrease the wavelength and decrease frequency, so our range resolution increases, and we can go to the final fine-grained body movements as well. So we can even detect like the heart movement as well. We haven't explored the heart movement, but still we would like to go for that as well.
Thank you. And the next question is, what are the options of signal processing algorithms for vital sign monitoring using radar?
Yeah, so for instance, like some specific signal processing algorithms.
Yes, I mean, the question is about the different options of signal processing algorithms.
Yeah, so my personal understanding is like these the short time Fourier transform. So that provides us the spectrogram or time frequency analysis, I think. So even the short time Fourier transform can help us in detecting these heart movements. So you can see as well, this is the microdoppler signatures obtained after applying STFT. So I think that can give we can even like use that as well. And then using these signatures, using machine learning or deep learning algorithms to classify different different heartbeat patterns. Are you with me, please?
Right. Yeah. Thank you. Then there's another question regarding the thesis opportunities. So you have mentioned one opportunity about the PhD. Can you also suggest some special topics in health monitoring that a master degree student can pursue as his thesis topic?
Yeah, that's very interesting. Yeah, thank you so much for asking this question. So we have like so many open areas. So for instance, anybody can explore, for instance, using radar sensing to monitor gate patterns, and then more monitoring some of the patterns that leads to critical events such as falls. So maybe instead of like being reactive, we can also look into some of the gate patterns and do predictions rather than detection in terms of like fault detection. So this can be one of the thesis topics. So the student can explore like different machine learning algorithms to analyze these patterns, I think. So this is the one of the, I think, thesis one can do.
Right. Regarding the integration of RF and the machine learning, how you comment this the incorporation of machine learning with the RF technology?
Yeah, machine, because without, I think, even for instance, there are some of the instances I can, yeah, I mentioned over here, but there are some of the instances, for example, visually, you can see, can you see this slide, please?
Yeah, can you make it full screen, please? It's not full screen.
Yeah, yeah, can you see it, please?
Oh, yes, yes, yes. Please carry on.
Yeah, so you can also see here, there are some of the instances in time, for instance, where some of the amplitudes level for different activities are similar. For example, you can see here as well, here, the activity for walking fast and sitting down is nearly the same in terms of amplitude information. So these are some of the visually you cannot detect. So for that you need machine learning classifier to perform to classify. And also some of the instances, for example, how to differentiate voluntary stop from freezing of gait, because freezing of gait is in practice it's also a stop, like the person stops walking. So these are the some of the instances like visually you cannot sometimes differentiate. So for that you need machine learning algorithms to classify it for you, because some of the intricate movements that you cannot classify visually. So you need machine learning, and also it also puts your machine learning classifier to the test as well. For instance, similar activities, the micro Doppler signatures. For instance, I can show here as well. For similar activities, if for instance a person is bending down to pick up something, you can see here there's a forward acceleration to the ground here, uh, the fourth figure. And then when the person is falling in frontal position, so you can see in both there is a, if you eliminate this one, the micro Doppler signatures from time 2.5 to 5, so you can see the signatures are quite identical. Or even here as well, bending down to tie shoelaces and also falling frontal fall as well, because visually and in practice these activities are quite similar. So visually you cannot classify which one is bending down to pick up something, bending down to tie shoelaces, and also which one is frontal fall. So you need machine learning classifier to do the task for you, rather than, because visually if anybody can see these signatures, they'll say, okay, like all of these three activities are for fall activities.
All right. When we talk about the machine learning, the first thing that came in mind is the data set, the availability of data set. So um, from where you get the amount of data that is suitable to perform the machine learning.
Yeah, so I mentioned, so we already have a public available data set using radar sensing. This one, anybody can download this data. So I think it's a huge amount of data. It's good for master, even for PhD thesis as well. It has 99 volunteers at 9 different locations. So there is plenty of room, plenty of stuff that need to be cooked with regards to this data set. So plenty of open areas. I'm happy to discuss that. If anybody wants to discuss, so please drop me an email as well. I'm happy to support and happy to discuss.
Yes, I think this is a very good opportunity. Can you please give a few examples of any commercial devices that are using these concept uh, or um, or any thing you have seen in the market that you are thinking to replace it with your RF device?
I'm conscious of one commercial available device in Coventry, Oxhome, I think Oxhome. So what they do, they don't use radar sensor. They use depth cameras to capture images, and also they use PIR sensor to pick up body temperature to monitor different activities in elderly people. To the best of my knowledge, I'm not aware of any commercially available device that monitors activities of daily living and detect falls in elderly using Wi-Fi sensing. For radar sensing, I'm not sure, but I'm not aware of to the best of my knowledge, I don't think so. There is any commercially available using Wi-Fi sensing. I know of many groups, they are trying to introduce Wi-Fi product. Even we are also trying for that as well.
Right. So when you
It's
talk
also,
about the camera based, uh, yeah.
yeah, please carry on.
Yeah, when you talk about the camera that particular device use a camera base, so how you compare the performance of a camera based device as compared to a RF device or
So
device based
camera
on radar?
based, yeah, camera based system. I don't think so. You need classification. Like if you are sitting in front of, like if you are watching these videos, so visually you can also interpret like which activity is which one. But the problem, like I mentioned, it's highly computationally expensive as well. Um, because if you are constantly recording images or videos, saving data in cloud, that is also one of the challenge. With Wi-Fi sensing, you only need like 4 or 5 numbers that which activity refers to which one, I think. So we haven't personally used uh, um, these vision-based systems or even the acoustic systems, but I am aware that they are highly computationally expensive. So I think performances are similar, but the challenges, I think, with vision-based system are more.
Right. So you mentioned in the last slide that there's a one PhD position available at your group. So can you please briefly describe also what is the requirement or what is your expectation from the student who will come to you for PhD in this program? So
Yeah,
it's
so
on
it's a
RF
fully.
based or machine learning base?
So it's both, I think, because but I'm looking for someone who is expert in RF antennas and propagation antenna design. Yes, there will be some part of machine learning, but that won't be that rigorous. So this PhD position was monitoring the vital signs for COVID-19 patients using non-contact, non-invasive method using software-defined radios. I have some of the examples I mentioned in my last slides. So this is a fully funded position. Anybody, but the only challenge with this position is because university requires students to have a minimum of 7 IELTS band. So that's one of the challenges I see. Other than that, so it's a normal process. I think any student. So I'm happy to share the link as well if anybody wants to apply.
Yes, I think definitely it's a very good research opportunity, especially the problem is very practical problem, and we all facing this problem at this moment of time. So it will be very interesting to work in this domain using the RF and RF facilities and maybe radars as well. So thank you, Dr. Aziz. And that's it from question from audience side and my side. And I would like to thank you very much for your time that you spare and gave a very useful talk on RF sensing for healthcare technologies. And we hope we will see you again at some other forums as well. And next year we are also holding the Pakistan first dedicated conference on RF and microwave, and hope you and your colleagues will come to Pakistan to present your work in this conference as well. Thank you,
Yeah,
Dr. Aziz, and see you in some other avenue. Thank you.
yeah. Thank you so much, Dr. Nishwan, for inviting me. Thank you.
Thank you. Thank you, audience, for joining us. Have a nice day. Bye.